Hi, in this lesson we're going to look at absolute value inequalities. Previously we already had a lesson on absolute value equations, so we're going to extend some of that knowledge here for an inequality. Let's start off looking at an absolute value inequality graphically. So we want to solve when the absolute value of x plus 4 is greater than or equal to 5. So it would be helpful to first figure out, well, when does this function equal 5? If we zoom in on the graph here, we can look for when the function is equal to 5. I'm going to mark that as a dotted line at 5. And so we can see that the function is equal to 5 here at -9 and at +1. So if this was an equation, those would be the two solutions. However, we're curious about when this function is greater than 5, greater than or equal to 5. And so that would be happening above 5. So all these outputs are above 5, but we care about the x's. We want to know when the function is greater than or equal to 5. And in that case, that's happening here for all of the x's before or to the left of -9 and to the right of +1. So we would describe that as x has to be less than or equal to -9, or x has to be greater than or equal to +1. Most of the time when we solve inequalities, we're going to write the solutions in interval notation. So for this interval notation, this would look like all the x's from -infinity up to -9 with a bracket, union, and then bracket +1 to infinity. This interval notation is helpful to describe a range of solutions. For the second one, we want to know when the absolute value is less than or equal to 9. So again, we care about when it's less than 9, but we can look at when it's equal to 9 first. And that dotted line here at 9 would show that the function is equal to 9 at -1 and here at +8. Now notice I'm using open circles here because we don't actually care about when the function's equal to 9. We care about when it's less than 9. And that's happening for this middle section for these x values. And those x values would be between -1 and +9. So one way to write that solution is to say x has to be less than 9 and greater than -1. Now reading it this way would say -1 is less than x, but x is also less than 9. We often write this as interval notation anyway, so I would write that solution as parentheses -1 to 9, both with parentheses, because our boundaries are not included. We don't care about when it's equal, and those 9, that should actually be an 8. All right, the x value is what we care about, and when x is 8, our output is 9. So change those 9s to an 8 for me. All right, we've got two more here graphically. So for number 3, we want to know when is the absolute value greater than or equal to -6. Let's put that little marking, that imaginary line for -6 again. If I care about when the function x plus 3, the absolute value of x plus 3, is greater than or equal to, it's never actually equal to -6, but it is always greater than -6. That's because the absolute value of something should come out as a positive number. So whatever comes out of this absolute value is guaranteed to be 0 or bigger. And that's what we're seeing here in this range of that function. all the numbers are 0 or bigger, which happen to all be greater than -6. So the solution for this one would be all real numbers. There are a few ways that you could write out that solution answer as all real numbers. One of them is in word format. Another is this set notation of an R, capital R, with 2 lines through it. But in interval notation, we just write that as -infinity to infinity. And you will be writing your answers in interval notation most of the time. Lastly, number 4 says the absolute value of x minus 1 has to be less than -1. Here is our -1. And the function, you can see, never actually equals -1, but it's also never less than, excuse me, it's never less than -1. That's because everything that comes out of the absolute value is positive, so this has no solution. There is no x that when I plug it in, I'm going to get an absolute value that comes out less than -1. So let's look at that algebraically now. When we think about the absolute value of something, let's say I have the absolute value of some mystery number. And I know that that number is greater than or equal to 5. If I ask myself what numbers, when I plug it in, the absolute value comes out greater than or equal to 5, I might think of 5, 6, 7, 8, 9, 10, keep going. So on a number line, all the numbers 5 and greater would satisfy that inequality. But those are not the only numbers. So when I also think about the absolute value equal to 5, we're asking ourselves what numbers are exactly 5 spaces away from 0. Well, that would be -5 and +5. So when we were doing equations, we looked at it in that format. But in an inequality, we have a range of solutions. So in fact, all the numbers to the left of -5 would also have an absolute value that's bigger than 5. If I took the absolute value of -6 here, it would come out as +6, which is greater than 5. So we have 2 sides to this solution region. Our solution would look like -infinity up to -5, union 5 to infinity. This is a compound inequality. And so when we look at the absolute value, there are several ways that you can approach that inequality. And right here, conceptually, we're just trying to understand what values would come out greater than or equal to 5, and that would be anything that's less than or equal to a -5 or greater than or equal to a +5. So conversely, what if we had something like the absolute value was less than or equal to 5? In this case, we're saying what values, when we plug it in, have an absolute value or a distance away from 0 that's 5 or less. So on a number line, that would be anything between -5 and +5. That would say that x has to be greater than or equal to -5 and also less than or equal to +5. So we can set up our 2 inequalities conceptually, understanding that the absolute value had to be less than or equal to 5, but the opposite would be greater than or equal to -5. So in the algebraic examples, I put some instructions at the top saying that we first want to isolate our absolute value bars. Always we want to get that absolute value by itself so that we can then use the definition of what absolute value is to create our 2 inequalities. One of those inequalities is going to look the same. The other is the negation, the negative version of that. And when you negate that inequality, it flips the inequality sign. So let's start with this first example. We have negative 8 minus 3 times the absolute value x minus 1 is greater than or equal to negative 32. So if we were isolating the absolute value, we first want to move this negative 8 by adding 8 to both sides. We can't combine the negative 8 and the negative 3 because that 3 is being multiplied to this absolute value. So we end up with negative 3 times the absolute value of x minus 1 is greater than or equal to negative 24. Because that negative 3 is multiplied, the inverse of that multiplication would be dividing by negative 3. So we're going to divide both sides by negative 3. And the absolute value of x minus 1 is less than or equal to positive 8. Notice that the sign changed, and that's because we divided by a negative. So if you need to write yourself a reminder, we always flip the inequality sign if we multiply or divide by a negative. Right, so we have isolated the absolute value. Now we want to apply that definition of what absolute value does. So I might think about this conceptually for a second and say the absolute value of something has to be less than or equal to 8. Well, that would only happen if that value is less than or equal to 8 and if that value was greater than or equal to negative 8. So it had to be between these 8s and negative 8s. Well, that inside, that question mark, is actually x minus 1. So we create our two inequalities. One of them says that x minus 1 is less than or equal to 8. And the other one says that x minus 1 has to be greater than or equal to negative 8. That leaves me with x is less than or equal to 9 and x is greater than or equal to negative 7 if we solve for x. It's helpful sometimes to put this on a number line so that we can write our interval notation. I would find negative 7 and positive 9 on my number line. Both of those are included because it says x has to be greater than or equal to or less than or equal to. The equal to's make these a closed circle. For x is less than or equal to 9, that would shade to the left of 9, but it also has to be greater than or equal to negative 7. So that would be to the right of negative 7. The values where x is less than or equal to 9 and also greater than or equal to negative 7 are between negative 7 and positive 9. So our solution is a region from negative 7 to 9. One way to write that solution is an inequality notation, like we're seeing here, x less than or equal to 9 and x is greater than or equal to negative 7, or an interval notation. The interval notation is what we are going to use, so we have bracket negative 7 to 9 bracket. All right, for number 2, we want to still isolate the absolute value. So we have the absolute value of 2 minus 3w divided by 4. So the absolute value is being divided by 4. We need to undo that division with multiplication. That leaves me with the absolute value 2 minus 3w is less than or equal to positive 8. So we get a similar inequality. I wanted to give you another one that was less than or equal to 8. Because what that tells us is if we had the absolute value of some number and it had to be less than or equal to 8, the only way that happens is if that inside number is less than or equal to 8 and if it was greater than or equal to negative 8. So that inside was 2 minus 3w. I set up my inequalities. 2 minus 3w is less than or equal to 8. Notice that the exact same inequality, but the negation of that, the negative version, would say 2 minus 3w could be less than or equal to, greater than or equal to negative 8. So notice that that sign changed to a greater than, and the 8 flipped to negative. So if you're just looking for a procedure of how this works, you create two inequalities where the first one has the same notation, just without the absolute value bars. But the second one is a negation of that absolute value. So it would say greater than or equal to, since I negated the inequality sign, it flipped it, and that 8 became a negative 8. So then we solve our resulting inequalities. That says negative 3 is less than or equal to 6 if I subtract 2 from both sides. Dividing by a negative 3 flips the inequality sign, and 6 divided by negative 3 is negative 2. So w has to be greater than or equal to negative 2. Then we solve the other inequality. Adding or subtracting 2 from both sides gives me negative 10. Dividing by negative 3 flips the inequality sign and makes that 10 thirds. You will have fractions. You can leave them as that improper fraction. But on the number line, negative 2 is going to be to the left of wherever 10 thirds is. And we are including both of those boundary values. W has to be greater than or equal to negative 2, but also less than or equal to 10 thirds. So we get the solution here in the middle between the two. Our solution would say bracket negative 2 to 10 thirds with a bracket on the end. All right, let's do two more, and then I'll let you kind of try some on your own. For 3, we have the absolute value of 4 minus 3c is greater than 6. So the absolute value is already isolated. If we think about this conceptually, we're wondering, what could that inside be and still have an absolute value greater than 6? That would happen if the inside was greater than 6, like 7, 8, 9, 10, or if the inside was less than negative 6, something further away from 0, being like negative 7, negative 8, all those are less than negative 6. So we use that conceptually to set up the two inequalities, or we just use the procedure and say that 4 minus 3c has to be greater than 6, or 4 minus 3c has to be less than negative 6. So we follow that procedure each time, where one inequality looks exactly the same, except there's no absolute value. And then the other inequality is the negative version, so that 6 became a negative 6. However, when we negate that, it flipped the sign to less than. You can follow either the conceptual way or the procedural way, but you'll still have two inequalities that should show up. So now, when we solve this inequality, we would subtract 4 and get 2. Divide by negative 3 flips the sign, and c is less than negative 2 thirds. We subtract 4 over here on the other inequality, and we get negative 10. Divide by negative 3 flips the inequality and gets me to positive 10 thirds. So now we have an inequality, or a number line, sorry, that starts at negative 2 thirds and positive 10 thirds somewhere. Those are not included in the solution because the solution doesn't say or equal to negative 2 thirds. It's strictly less than negative 2/3 to the left of that, or greater than 10/3 to the right of that. So we write that out in interval notation. Your solution would be parentheses negative infinity all the way to negative 2/3 with a parentheses. Union, and then we do again parentheses 10/3 to infinity with a parentheses. All right, and for number 4, we have negative 4 times the absolute value, 4 minus x, is greater than or equal to negative 12. Again, we need to isolate the absolute value. So you want to get that absolute value by itself. We would divide by negative 4. Dividing by negative because we are undoing multiplication. We cannot distribute into absolute value. What we're trying to do is isolate the absolute value and when we divide by a negative, see I forgot to do it there, but we divided by a negative, we have to flip our inequality sign. So this changes to a less than or equal to 3. Now, conceptually, we're saying if I had the absolute value of something and it had to be less than or equal to 3, what values would that be? Well, that could be something like 1. Absolute value of 1 is less than 3, or 2. But it could also be negative 1 or negative 2 or even 0. So that inequality would say anything that's less than or equal to 3 and also anything that is greater than or equal to negative 3. We set up that conceptually, or we go straight to the procedures and we think that 4 minus x has to be less than or equal to 3, and 4 minus x is greater than or equal to negative 3. We solve our inequality by subtracting 4. 3 minus 4 is negative 1. That leaves me with negative x, so that's a negative 1. We divide by negative 1. Dividing by a negative flips our inequality, so it says x is greater than or equal to positive 1. On the other inequality, I still subtract 4 and get negative 7. Divide by negative 1 again. X has to be less than or equal to a positive 7. On a number line, we would find positive 1 and positive 7. Those values are included because our inequalities say or equal to. And we're looking for the values that are greater than 1 and also less than positive 7. So that interval notation should say, let's write solution here, but it should say bracket 1 to 7 with a bracket. All right, so there are 2 examples on the next page for you to try on your own. They're up here. You can pause the video and go ahead and attempt them. When you're ready, you can hit play. If you just need these worked out a little bit more, I'll go ahead and do them now. So I would add 8 to both sides and get 2c plus 6 is greater than positive 4 because we've added 8 to both sides. Then we set up our 2 inequalities. One of them says 2c plus 6 is greater than 4, and the other one, or 2c plus 6 is less than negative 4. If I continue to solve for c with each inequality, we would subtract 6 and get negative 2, divide by 2 and get negative 1. Notice I didn't flip the sign because we didn't divide by a negative, we divided by a positive 2. All right, and then subtract 6 here, we get negative 10, divide by 2, we get negative 5. So c has to be greater than negative 1 or less than negative 5. On a number line, negative 5 happens before we get to negative 1. Neither one of them is included, so we have 2 open circles. x has to be greater than -1 or less than -5. So in that interval notation, you should have parentheses -infinity up to -5 with the parentheses, union, and then -1 to infinity, both with parentheses. And for number 6, we have 4 minus 5 times the absolute value, 2y minus 7, is greater than or equal to 0. I would subtract 4 from both sides and get -5 times the absolute value is greater than or equal to -4. Dividing by -5 puts the absolute value 2y minus 7 less than or equal to 4/5. So even though we have a fraction, it still is a number. We continue the same process. We set up our two inequalities. One of those inequalities looks exactly the same. 2y minus 7 is less than or equal to 4/5. And we have 2y minus 7 is greater than or equal to -4/5. So at this point, if you need the calculator, you can use the calculator, but you're trying to figure out what is 4/5 plus 7. You could get a common denominator and add them, but we do get 39/5. So 2y is less than or equal to 39/5. If I divide by 2, we get 39/5 divided by 2, which is 39/10. You can write it out that way, or you can write it as 3.9. You could use your calculator to get that. So what I did was take that 39/5 and divide by 2 is 39/10. That is approximately or exactly 3.9. Then the other inequality, we have -4/5 plus 7. So -4/5, and we're adding 7 to it, gives me a positive 31/5. We divide by 2 again, so y is greater than or equal to 31/10, which is 3.1. Now we would put those on a number line, 3.1 and 3.9. These are included, and we would shade between. So your solution should have brackets in your answer. We have bracket 3.1 to 3.9 with a bracket. All right, there are two special cases at the end here. Special case number 7. All right, this says 3 times the absolute value 5 minus 9a is greater than -93. You would still isolate your absolute value. So we want to get the absolute excuse me, we want to get the absolute value by itself. I would divide both sides by 3. Dividing -93 by 3 still leaves me with a -31. Now, I don't really want to go straight into our inequalities. And this is why I like doing this conceptually, because we're trying to figure out the absolute value of what number is greater than -31. If we think about this conceptually, anything I put inside this absolute value is going to come out as 0 or bigger, 0 or positive. So all of those outputs are actually bigger than -31, no matter what we put in. So this one is actually all real numbers. Our solution is -infinity to infinity, because everything that's coming out of this absolute value will be greater than -31. This is what was happening graphically. We were looking at that one example here, the absolute value was always greater than that negative, so the solution was all real numbers. In number 8, if I isolate the absolute value, we would multiply by 9 and get absolute value negative 9 minus 4k is less than or equal to negative 9. So we pause again and think about this conceptually. If you had the absolute value of something is less than or equal to negative 9, there's no way that happens. Nothing that I can plug in will have an absolute value that comes out less than negative 9. The absolute value is always going to come out as 0 or positive, and those values are never less than negative 9. They're always greater. So this actually has no solution. The output of that absolute value will always be positive. So if you need to write yourself some explanation, I would have off to the side something like the output of this absolute value running out of room. That does say absolute value. Will always be 0 or positive. If it's always 0 or positive, then it will never be less than negative 9. No matter what we plug in. If I plugged in positive 2, the positive 2 has the absolute value of positive 2, and 2 is not less than negative 9. So maybe we try something like negative 10, but the absolute value of negative 10 is positive 10, and that's still not less than negative 9. No matter what I plug in, it's never going to have a solution that's less than negative 9. All right, now these do have some application type questions. Sometimes we see this with a tolerance or a margin of error type thing. And this word problem says that Maria wants to purchase pavers for her garden. She determines that each paver is within a 1/4 inch of the stated length of 16 inches. So she's going to line the pavers end to end with no space between them to create a straight path in her garden. We can write an absolute value inequality that can be used to find the possible lengths of the pavers. So that's our goal, is to look at the length of a paver. And each paver is within a 1/4 inch of 16 inches. So the amount that we could be off by is plus or minus a 1/4 inch. So it's saying we are roughly around 16 inches plus or minus a 1/4 inch, which would be 0.25. The way we write this is looking at the absolute value of the actual minus the expected is less than or equal to our tolerance. Because we get this plus or minus thing, 0.25, from that tolerance. We can be within plus or minus 0.25. So we're within a distance or a difference, of the actual minus the expected 16 inches. So we'd say the actual thing minus the 16, that difference has to be less than or equal to a 1/4 inch, 0.25. And there's our inequality. All right, so there are some practice problems that are posted, and you can work through those to kind of gauge your understanding.